Good afternoon, everyone, and thanks for attending my talk, diving into Spooler, discovering LPE and RCE vulnerabilities in Windows printer drivers. My name is Zhiniang Peng, and this is a joint work with ZeSen. First of all, please allow us to introduce ourselves. My name is Zhiniang Peng, also known as Edward Peng in Twitter. And I'm an associate professor for Huazhong University of Science and Technology. And in the meantime, I'm also a security researcher at Cyber Kunlun. I got my PhD degree in cryptography, but actually I'm interested in all areas of computer science. I work in both defensive and offensive security. Previously, I have published many research in both industry and academia. To get more information about me, you can find it in my personal Google site. And I'm also a bug hunter in the past 6 years. Here are some of my bugs in the past 6 years. Most of the time I'm doing vulnerability hunting on Windows or some web applications. And today I'm going to talk about how do we find some of those bugs in Spooler. And this page is about my coworker, ZeSen. He is a security researcher at Cyber Kunlun, and now he focuses on fuzzing and Windows application security. Here is the agenda of this talk. First, we will give an introduction to the Spooler and the Spooler bugs. Then we will talk about the new attack surface we found in Spooler, the Windows printer driver rendering. After that, we will dive into the XPX format and found vulnerability in it. First, the introduction. In this session, I will give an introduction to the print Spooler service and its vulnerability in the past. So what is a Spooler? Spooler is actually a Windows service. It is a dedicated program and software that essentially manages the order of the documents to process to the printer. Just like the picture shows, Print Spooler allows you to send the documents to the printer, and where some other one is still printing, but it holds it in the queue until the current job has been finished. Spooler actually doing more than that. Print Spooler in Windows actually has more things to do than just spawning and print document. It exposes the functionality for add or remove a new printer and allow users to configure this new printer. Support high-level function call into print jobs, receive printer jobs, and schedule the print jobs for printing. Windows printer is based on the Windows RPC. By using the export RPC interface, a user can add a new printer and can fully control the printer. Then we can configure this printer, create some print jobs, printer jobs to a printer port, or manage those printer jobs. All of the above are completed by the high privilege process Spore S3.x. The main component of the RPC call is local SPL.del, but the client can actually interact with the Spooler locally or remotely, which will provide us local and remote attack surface. We are not going to talk too much of the basic of the Spooler, but there has been a lot of public research about the print Spooler before. I suggest you can read them by yourself after the talk. Print Spooler is very hot in cybersecurity. There are many reasons for it. First, the Spooler used to run with very high privilege and load code from network, which is prone to security issues. Second, printer bugs account for 9% of all Windows cases reported to Microsoft, according to MSRC blogs. Third, there are a lot exploited vulnerability in Spooler in the past few years. And some of the vulnerability is very high impact and attract a lot of attention. For example, the stun-next printer exploitation and the print nightmare bugs, and so on. For last 14 years, there are a lot of printer bug has been exploited in the wild. And this picture shows its history. The vulnerabilities in printer are numerous, but most of all the famous bug, but almost all the famous bugs follow some familiar pattern in the past, including the path redirection attack, the path traversal vulnerability, the arbitrary DEL loading bugs, and the memory corruption bugs, and some other logical bugs. Due to the extensive file operation performed by the printer, the majority of those vulnerabilities are used to based on symbolic link attack in Windows. Among those vulnerabilities, print nightmare is one of the very expensive one, as it's easy to export, stable, and can lead to remote code execution on Windows operating systems. This is an example of the print nightmare. The cause of print nightmare is improper checks in printer's RPC interface function. When an attacker sends a special craft RPC to the remote print server, it can cause the server to load a malicious DEL located on the attacker machine, leading to remote code execution. For more story about this bug, we refer you to watch our previous talk in Black Hat US 2021. But after print nightmare, Microsoft has put a lot of effort in fixing printer bugs. In 2022, Microsoft has fixed 33 vulnerability for print Spooler. And some of Microsoft fix even broken the print Spooler for many times, which causing usability issues. Except fixing bugs, Microsoft also introduced many new mitigations for print Spooler. For example, it has added junction redirection protection to block path redirection attacks. And it also adds signature checks to prevent arbitrary DEL loading, which was abused before. This will make exporting the print Spooler much harder. Is Spooler secure after all the fix? Last year, we decided to dive into Spooler again and try to find some new bug. So let's start our new journey on the Spooler. The new attack surface, Windows printer driver rendering. When exploring new attack surface, we prefer to look at the architecture. And in this time, we find that the rendering component, it seems that it has not been deeply researched before, although Spooler has been researched for many, many years. In our experience, complex rendering module often have many bugs, so we decided to explore this area. We will begin our introduction with a common print example. In our daily life when using printers, we often need to print a document. We will open a document, for example, in Word. Then we select the printer driver and process to print. In this context, the print driver plays the role of the rendering, just like the picture shows. Let's break down this scenario in more details. Word is a common GUI application which is used in usual mode. It will use the Microsoft XPX document converter to transform the document into XPX format. Then it sends the RPC call to the Spooler. The Spooler will use the XPX spool to save and rendering using the Spooler driver. The rendering process converts the XPX format into print control language, which is a language used by the printer device. Printer operates in two modes, V3 mode and V4 mode. The V3 mode is the older one. It is directly used by the Spooler service to load the printer driver and perform the rendering. And for the V4 mode, it will create a sub-process print filter pipe service to load the printer driver and do the rendering. A crash in V3 mode can cause the entire printer service to become denied of service. While in V4 mode, it would only result in the restart of a single process. So what impact could a rendering vulnerability have? So our answer is a local privilege exploitation, LPE, and remote code execution, RCE. Here is an attack scenario. First, let's look at the LPE attack scenario. It allows the local user to elevate their privilege to the system level. The attacker will use a print API to send malicious XPX to the print drivers. When the driver rendering these evil XPX files, it will be exported, then get the system privilege. Then we want to introduce a remote code execution attack scenario. An authenticated attacker with normal privilege could also send a modified XPX file to a shared printer, which can result in remote code execution. The attacker will use a print API to send malicious XPX to the shared printer over SMB or some other method. When the printer driver rendering this evil XPX file, and it will be exported as RCE. In addition to normal RPC call remotely, the vulnerability can also trigger using remote desktop protocol, RDP. First, the attacker needs to convince the victim to connect to the remote desktop server. Then the attacker can use the remote desktop print channel to connect the victim's printer driver. So the attacker can use the print API to request a malicious print job to achieve remote code execution. And the next part, dive into the XPX format, so we can find some vulnerability here. Here I will hand over the talk to my coworker, ZeSen, but however, he cannot be here on site because of the visa issues, but he has recorded his talk.
Hi everyone, I am ZeSen. The next session will be presented by me. Let's dive into the SPS format. The full name of SPS is the Open XML Paper Specification. It's an open specification for a page description language and a fixed document format. As the name suggests, it's an open XML format. This format is widely used in Office applications. It uses deep compression technology to store documents. When we extract the SPS field, we will get the XML field and some resource field. The XML field is important in this format, as it outlines the content on each page. Let me give an example to show how it works. The XML content in the square will create a page like this when it's ranked. In the previous session on attack survey, we talked about print document using the Word application, which relies on the GDI print API. This method requires converting other formats to SPS before printing, which is slow and doesn't allow for precise control over the SPS content. So we prefer to use the SPS print API to directly tap the SPS file to the Spooler service. In Windows 10, we can use the SPS viewer comes pre-installed in Windows to open the SPS file and send them to the printer. However, the SPS didn't become popular, and Microsoft has removed its support. But we can make our own application to use the SPS print API. The most important function in the SPS print API is the star SPS print job. It connects to a printer using the printer's name as a parameter. If you need to connect a remote printer, you have to enter the SMB port. Then we will use the document string to send our SPS file into the document using the iStringRead function. With the introduction and preparation out of the way, let's begin our journey to discover vulnerabilities. The first part is vulnerabilities in resource parsing. Just like the most rendering formats, SPS also supports custom embed fonts, but they need to be obfuscated. Here we use a simple diagram to explain the deep obfuscation. It uses the file name as a key to perform an SOR operation with the first 32 bytes of the font. There are so many research on font before, so we won't discuss the detail of font today. We primarily refer to one font vulnerability to rule them all, posted by Mercy Guru Jack or Google Project Zero. This article has provided us with a lot of valuable information. We discovered 9 CVEs in the font parsing with Microsoft print driver rendering. 4 CVEs are remote code execution vulnerability. 5 CVEs are information disclosure vulnerabilities. Here we choose 2 vulnerabilities to introduce. First one is CVE 2023-24863, Microsoft Postgres and PCLC's class print driver information disclosure vulnerability. It's an out-of-box read vulnerability in true type parsing, and the offset was not checked during the parsing of the table. It's a common vulnerability pattern in font parsing. And the unique point here is the crash code stack. It will crash in the string buffer write. The function string buffer write is actually used for the output string, so it will write out-of-box data to the output file. In this way, we can easily turn it into an information leak. The second case is the CVE 2023-23403 Microsoft Postgres and PCLC's class print driver remote code execution vulnerability. It's an out-of-box write vulnerability in OpenType parsing. In the OpenType format, a special table is the CFF table. The CFF table stands for the Compact Font Format, which is a compressed font data format, as known as Postgres Type 1 fonts. In the CFF format specification, we found the statement: an operator may be preceded by up to a max of 48 operators. However, whether the code correctly checks for this is our question. So we conducted the test and found that there was no check here. The code directly allocated an area of sys height 48, but did not perform any checks. If there are more than 48 operators, it will result in an out-of-bounds write. The second part of resource parsing is the color management. The color management is supported in V4 print drivers. The common resource field is the ICC profile, which full name is International Color Consortium Color Profiles. The intent of this format is to provide a cross-platform device profile format. The ICC profile is used in the XML to describe the page. We will modify the previous example by replacing the default colors with an ICC profile to ensure the same color representation across different devices. Next, we need to learn about the format of the ICC profile. The standard way is to read specification. We found that the ICC format is similar to fonts, but we only have limited public resources available. They will require more time for document reading and reverse engineering. However, we don't want to spend too much time learning the format. So we need a method to discover vulnerabilities more quickly. The method we chose is fuzzing. We first saw a WinFL, which is the most common fuzzing tool for the Windows platform, but we did not succeed. The ideal scenario for WinFL, as shown by the orange square, is to use an application as the harness to load the target library and then call the target function. However, the scenario of print driver rendering is that we use our application to send the RPC call to the Spooler service, and the Spooler service will create the sub-process print filter pipeline service to load the target driver and then rendering. It's quite challenging to write a harness to load print driver and run directly. Next, we try using waterfalls, developed by Overclock. It's a distributed code coverage guide, customizable cross-platform snapshot-based fuzz, designed for attacking user and kernel mode targets running on Microsoft Windows. It seems very suitable for our needs. In this fuzzing process, we need to set a breakpoint in the parsing of the resource code, set the snapshot, and then use the fuzzer to start fuzzing from the snapshot. This fuzzer enables us to complete fuzzing under the print driver, and we are thankful for the great fuzzer. We discovered 9 CVEs in the ICC profile parsing with the Microsoft Print driver rendering. 8 CVEs are remote code execution vulnerability. Only one CVE is the information disclosure vulnerability. Here we will introduce the vulnerability pattern using a specific case. The case is the CVE 2023-24909 Microsoft Postgre and PCLC's class print driver remote code execution vulnerability. It's an integrated overflow vulnerability. It was happened in parsing the profile description tag. The tag in this context will use the length field to describe the size of the stone buffer, but the code lacks the check against the length. If the length is smaller than the buffer size, we result an out-of-box read. And if the length is very large, causing an integrated overflow, it leads to an out-of-box write. The second part is vulnerabilities in XML parsing. Let's briefly review XML in SPS. It's quite different when it comes to parsing resource in XML. The resource file is in binary format, which is hard to read directly, but easy to mutate for parsing. On the other hand, XML is easy to read, but not as easy to mutate. For the resource file, they can perform the same function across different applications, make them easy to connect. But the XML files are designed specifically for software, and the direct use of the SPS field is not widespread, making it difficult to connect. So we had to generate the XML file ourselves. We need to read a 496-page SPS document and then create the corresponding XML. But we don't want to do that. Instead, we aim to automate the generation process. We found that the document includes an SSD field, which is typically used for validating XML formats. Can we review the process and use the XSD to generate the XML? We made the following try. First, using the SSD to extract the tags and adding some mutation allotment to generate the corresponding XML. Then we package it together with other resource formats into an SPS file. However, the fields generated this way sometimes does not meet the requirements for the print driver rendering. We need to debug and perform reverse engineering to determine the cause. In this process, we found that the print driver renderings records the error logs. So we want to use the error log to improve our document. we may try to send the errors log along with the SPS document to the large language model to repair the XML file. This way helps us save some time to repair the documents. Here we discovered more vulnerabilities and obtained 12 CVEs. Most of them is the remote code execution vulnerability. We appreciate Microsoft's effort in fixing all the vulnerabilities. We will introduce the vulnerability pattern using a specific case. The case is CVE 2023-24927. The weakness of the vulnerability is type confusion. The yellow square here describes a correct XML and the calling process. During the rendering, the SANL parse draw function is called to parse the tag step by step. If the true tag of parse stroke is solid color brush, the corresponding offset function of the table SANL solid color brush drop is called. However, if our parse stroke lacks a true tag, you will call an incorrect function in the table, leading to a type confusion vulnerability. After our effect, we report many vulnerability cases to Microsoft. They realized there were many problems with the attack surface and took action to fix the document. We start to wonder if that was enough. So we shift our focus to test the print drivers or other companies. So the third part is vulnerability in third-party driver. After investigating several common print companies, we found that some still depend on Microsoft disconnected drivers for their printing, while others had implemented their own custom drivers. Some companies use their own printer drivers, such as HP, Dell, and Canon, while others still rely on Microsoft's print drivers like Qsera. We discovered vulnerabilities in these custom print drivers and report them to their security departments such as HP. Microsoft has now enabled a new architecture for printers called Windows Protected Print Mode. In this mode, loading third-party models is not allowed. SPS rendering will be performed under users' permissions. Common Spooler task privilege will be downgraded, and many mitigations has been added. As shown in the diagram, printer-related tasks are now handled by Spooler worker.s, which runs in a restricted service context rather than system. The Windows Protected Print Mode will significantly reduce the attack surface of printers and mitigate the impact of vulnerability. Next, I will hand the microphone back to my coworker Zhiniang Peng to summarize.
Okay, the last part, the summary. So in this talk, we review some of the old bugs for Print Spooler, and we diving into Print Spooler again and find a new attack surface in it. By diving into this new attack surface, we find more than 13 CVE in Prince Spooler, which is RCE and LPE vulnerability in Windows. And those bugs happens in resource parsing, XML parsing of Windows driver printer. And we also find some bugs in third-party printer drivers. So the takeaways, you can always find some new attack surface if you really dive into it. The Prince Spooler service is researched for many years by security researcher, but it still has so many bugs. So if you really dive into some attack surface deep enough, you can find new bugs. And that's the most important is, as I always say, disable your Spooler if you don't need it. And that's all for my talk. Thanks for listening.